In the summer of 1957, something incredible happened in the Nevada desert. During a routine underground nuclear test, a 900-kilogram steel plate was blasted into the sky. High-speed cameras caught it for only a single frame. Calculations suggest it was moving at 66 kilometers per second. That is 6 times the escape velocity of Earth. While physics tells us it likely vaporized in the atmosphere, this accidental experiment proved something terrifying. We had discovered a source of power so immense that it could throw heavy metal into the cosmos effortlessly. It sparked a question that haunted engineers for decades. What if we could harness that destructive force? What if we stopped building rockets like fireworks and started building them like bombs? For over 70 years, humanity has possessed the key to the solar system. We have the technology to reach Mars in weeks, not the agonizing months that current missions require. We could have been walking on the moons of Saturn by 1980, but we chose not to use it. The story of nuclear propulsion is one of brilliance, fear, and missed opportunities. It is a tale that takes us from the height of the Cold War to the cutting-edge fusion startups of 2026. And it begins with the most audacious engineering project ever conceived by the human mind.
The concept sounds like the ravings of a madman. You take a spacecraft the size of an office building, you load it with thousands of nuclear bombs, and then you detonate them, one by one, right behind your own ship. This was Project Orion. It wasn't science fiction. It was a serious, well-funded program led by some of the smartest physicists in the world. The engineering challenges were immediately obvious. How do you keep the ship from vaporizing instantly? The solution they found was shockingly simple. They designed a massive steel pusher plate mounted on the back of the vessel. It would take the brunt of the nuclear fire. But they needed a way to feed these bombs out of the ship rapidly and reliably. They needed a mechanism that would never jam, no matter how fast it fired. So they turned to an unlikely source for help. They consulted engineers from Coca-Cola. The logic was undeniable. Coca-Cola had perfected the technology for handling and dispensing cylindrical cans at high speeds. If you can dispense a soda without jamming, you can dispense a nuclear pulse unit. The scale of these designs was staggering. A standard chemical rocket is mostly fuel tank, but an Orion ship would be a true deep space vessel. The 4,000-ton reference design could deliver over 1,000 tons to orbit. To put that in perspective, that is more than the entire International Space Station in a single launch. It offered a combination of thrust and efficiency that chemical rockets can only dream of. But there was a catch. To make it work, you had to detonate a nuclear weapon every second. You would be riding a machine gun of atomic blasts all the way to the stars.
The physics of survival were the first hurdle. When a nuclear bomb goes off, it creates a sphere of plasma hotter than the sun. Most people assumed this would melt anything nearby, but the engineers at General Atomics discovered a secret. During a test involving steel spheres coated in graphite, they found something unexpected. The spheres survived the blast. The intense heat vaporized the outer layer of graphite instantly, this creating a protective gas shield that insulated the object for the few milliseconds that mattered. They realized they could do the same for the ship. By spraying a thin layer of oil or grease onto the pusher plate between shots, they could prevent it from melting. It was a brilliant solution found by accident when someone left oily fingerprints on a test plate. The next problem was the G-force. Getting hit by a nuclear explosion is like getting kicked by a giant. The acceleration spikes would turn a human crew into jelly, so they designed a 2-stage shock absorber system. Imagine a giant pogo stick connecting the pusher plate to the rest of the ship. The plate would slam forward violently, but the shock absorbers would smooth that energy out. The crew in the upper decks would feel a rhythmic pulsing, like riding a train over a bumpy track.
They built scale models using conventional explosives. One model, nicknamed the Hot Rod, actually flew in 1959. It popped up into the air on a series of sharp blasts, proving the concept was stable. It was ugly, it was loud, and it was incredibly violent. But the math proved one undeniable fact. It would have worked. We had the technology in 1960 to build a ship that could reach Saturn in months. But as the engineering problems were solved, a much darker issue began to emerge.
The line between exploration and destruction is thin. While the scientists dreamed of visiting Mars, the military saw something else entirely. The U.S. Air Force looked at the Orion design and saw the ultimate battleship. They envisioned a vehicle armed with nuclear missiles, impenetrable shielding, and directed energy weapons. One concept was particularly terrifying. It was known as the Doomsday Orion. This was a single-stage vehicle designed to lift a payload of over 1,000 tons. But that payload wasn't supplies or colonists. It was a single thermonuclear warhead. We are talking about a yield exceeding 8 gigatons. If detonated in orbit, it would have scorched a continent-sized area of the planet. It was a weapon so powerful it rendered all other warfare obsolete. This militarization terrified the scientists involved. Freeman Dyson, one of the project's leaders, began to have second thoughts. He calculated the cost of launching an Orion ship from the ground. The radioactive fallout alone would statistically cause fatal cancers for up to 10 people per launch. That might sound low to some military planners, but to a physicist like Dyson, it was ethically unacceptable. The death knell came in 1963. The Partial Nuclear Test Ban Treaty was signed, outlawing nuclear explosions in space. It was a victory for planetary safety, but a tragedy for space exploration. Project Orion was officially dead by 1965. NASA chose the chemical rockets of the Apollo program instead. They were safer, cleaner, and politically palatable, but they were also a dead end for deep space travel. We traded the stars for safety, and for 50 years, nuclear propulsion went into hibernation.
But the dream didn't die completely. If we couldn't use explosions, maybe we could use a slow burn. This led to the development of nuclear thermal propulsion. Instead of dropping bombs, you use a nuclear reactor to heat up hydrogen. It is a much more civilized way to fly. You pump liquid hydrogen through a scorching hot reactor core. It expands rapidly and shoots out the nozzle. Because hydrogen is so light, it moves incredibly fast. This gives you twice the efficiency of the best chemical rockets. In the 1960s, the NERVA program built and tested these engines. They worked beautifully. They didn't explode, they didn't spread fallout, and they were ready for Mars. But politics intervened again. After the moon landings, public interest in space collapsed. The budget for a Mars mission evaporated, and NERVA was canceled in 1973. It seemed like the technology was cursed. Fast forward to the 2020s. We thought the nuclear age was finally returning. NASA and DARPA announced a groundbreaking project called DRACO. The goal was to launch a nuclear thermal rocket into orbit by 2027. It felt like we were finally picking up where the 1960s left off. Contracts were awarded to Lockheed Martin. Designs were finalized. The hardware was being built. But then, in mid-2025, history repeated itself. The program was suddenly and quietly canceled. But this time, it wasn't fear of radiation that killed it. It was something much more mundane.
The cancellation of DRACO in 2025 caught many enthusiasts by surprise. But if you look at the economics, it makes perfect sense.
The space industry has changed fundamentally. In the 1960s, launching mass into orbit was incredibly expensive. You needed high-efficiency engines because every kilogram of fuel cost a fortune to launch. But today, we live in the era of the Starship. SpaceX has driven the cost of launch down so aggressively that the old rules no longer apply. Why spend billions developing a complex nuclear engine when you can just launch a massive chemical rocket? The government analysis was brutal. They concluded that the return on investment for nuclear thermal just wasn't there anymore for cislunar space. Chemical rockets are now cheap enough to do the job between the Earth and the Moon. It is a classic case of good being the enemy of perfect. Starship is good enough, so the perfect efficiency of nuclear engines was deemed unnecessary luxury. This decision effectively killed government-led fission propulsion for the foreseeable future. The NASA budget for 2026 requested zero funding for the technology. It seems we are stuck with chemical fire for a little longer. But while the government retreats, a new player has entered the game, and they aren't interested in splitting atoms. They want to smash them together.
With the government stepping back, the private sector is stepping up. And they are aiming for the holy grail of energy, fusion. Companies like Pulsar Fusion in the UK and Helicity Space in the US are making bold moves. They have secured funding and partnerships that were unimaginable a decade ago. Fusion propulsion is a completely different beast from the fission systems of the past. Instead of a radioactive core, you use magnets to trap superheated plasma. You squeeze isotopes until they fuse, releasing vast amounts of energy. The exhaust velocity is astronomical. We are talking about specific impulses 10 times higher than the best nuclear thermal engines. Pulsar Fusion claims their direct fusion drive could cut the trip to Mars down to 30 days. They recently opened a facility in Texas to tap into the American aerospace market. They're targeting an orbital test as early as 2027. But we need to be realistic. Fusion is notoriously difficult. Containing plasma that behaves like a chaotic weather system is one of the hardest problems in physics. Startups often have aggressive timelines that slip by years or decades. However, the fact that private money is flowing into this sector is a massive shift. It suggests that the market sees value where the government saw only risk. And while propulsion struggles, nuclear power is finding a different foothold in space. It turns out the next nuclear race isn't about moving ships, it is about keeping the lights on. While rockets might remain chemical for now, the surface of the Moon is going nuclear. Solar power has a major weakness on the Moon. The lunar night lasts for 14 Earth days. Batteries simply cannot bridge that gap for a large human settlement. If you want a permanent base, you need a nuclear reactor. This has triggered a quiet but intense geopolitical race. In late 2025, the United States issued a directive mandating a lunar surface reactor by 2030. But they aren't the only ones. Russia and China have formalized their own plans. They're working together on the International Lunar Research Station. Their roadmap confirms the construction of a nuclear power plant on the Moon by 2035. This is the new space race. It is not about planting flags anymore. It's about infrastructure. Whoever controls the power supply controls the future of lunar development. Russia's space program has faced massive budget cuts, and their nuclear tug project, Zeus, has faced delays. But their nuclear expertise remains world-class. Combined with Chinese funding, this bloc represents a serious competitor to Western plans. We're moving toward a future where the Moon is dotted with glowing reactors. It's a necessary step. You cannot build a civilization on the Moon without reliable, high-density power. And once we have nuclear power on the surface, putting it back into our engines is the logical next step.
We stand at a strange crossroads in space exploration. Technologically, we could have been interstellar travelers decades ago. The physics of Project Orion were sound, the engineering of Nerva was proven, but fear and politics kept us grounded. Now, economic forces are keeping us reliant on chemical rockets. It is cheaper to burn methane than to split atoms. But this chemical dominance cannot last forever. If we truly want to go beyond Mars, if we want to reach the outer planets in a human lifetime, we have no choice. The tyranny of the rocket equation is absolute. Chemical fuel is simply too heavy and too inefficient for the deep void. The cancellation of DRACO is a setback, but it is likely just a pause. The rise of private fusion companies and the race for lunar nuclear power show that the atom is inevitable. We started this journey by blowing a manhole cover into history. It was a crude, violent beginning, but it showed us what was possible. One day, we will stop fearing the fire and learn to ride it. And when we do, the solar system will finally open up. Until then, we are just tourists standing on the shore, waiting for a ship that was designed 70 years ago.